Okay, the one we're going to see in a sec. All right, but this is actually relevant to today because I just showed you the forecast and it's abnormally warm, and then a couple weeks ago it was abnormally cold, so we're getting these strange effects, and of course this is part of the global warming thing, right? It's not always warmer, sometimes it's colder, but we get these erratic weather patterns. And is this normal, or is this just something we've observed in the last 50 years? I'm not getting into that debate, but what I do know for sure was it was only 2 degrees this morning. My car told me so. Yet the road was frosty. Doesn't water freeze at 0? So how does that work? Have you guys noticed this before? Yeah, the road, your windshield, you can scrape your windshield and you're like, you got a thermometer right there. It says 2.5 degrees. And you're like, well, what's going on here? Why does this happen? Magic? Magic. A little fairy comes down and goes, ding. The air is that cold. Okay, it is. We know it is because it's frozen. Is it the air though? Because isn't that what the thermometer tells us is the air temperature? One word. Radiation. Okay? This thermal energy that this windshield might have, it actually gets radiated to space. Because what's the temperature of space? A lot less than 2. It's a lot less than 0. Okay? I think the dark side of the moon, every time it turns around, it's like minus 160. And then the sun hits it and it gets up to something really, really warm. Okay? It's a lot more, it doesn't have an atmosphere around it, right? It doesn't contain, and an ocean, which we're going to speak about in a sec, doesn't contain its heat very well. Loses it very quickly, gains it very quickly. So that's what's going on. That's why your windshield can freeze even though it's 2 degrees out. It's because of radiation, right? It loses this heat, not by convection, not by conduction, because that's how the thermometer works, right? It's convection. It's the cloud of thermal energy coming over and surrounding that thermometer, telling you it's 2 degrees. Yet stuff still freezes. So that's why this happens. Specific heat capacity. There's a formula for this, and I'll show you what that means. And let's just look at this table. Water has a high specific heat capacity. What does it mean? It means it takes a lot of energy to raise 1 kilogram of water by 1 degree. It takes 4,200 joules to do that. It's very resistant to change its thermal energy. But you guys know the properties of metal. You know, if you take a metal rod and you stick it in the fire, I don't care how long this rod is, it could be 10 feet. I mean, what happens very, very quickly? You got to drop it because it gets hot. So it's a good conductor of electricity. That's why we use like copper and aluminum in the walls. Hopefully not aluminum these days, but there was a time when they used it quite a lot and we had problems. Okay? We don't want to, like when you're toasting your marshmallows, anyone used a metal stick? And like bad things happen, right? You want to use wood. A, because it doesn't heat up your hand, and B, because then the marshmallow doesn't slide up and down it like sometimes you do with a metal one. Look at metals. Copper doesn't take much energy, 430 joules, to raise a kilogram of it by 1 degree Celsius. Okay? So if you want things to stay at an even temperature, if you don't want them to overheat, like say your car engine, do you want to fill it with copper or do you want to fill it with water? Yeah, it absorbs a lot more heat, right? Okay, you don't want this thing to overheat because you see what happens on the highway when that happens, right? It breaks. You got to pull over or you're going to do serious damage to it. Most of them have safeguards in it. They just shut themselves off. There's a big, huge highway in California, and it's like, you know, even hotter than here. 120 Fahrenheit. What's that? 43, 44? and your car, you know, you got the air conditioner on full blast because you want to keep cool, you're working this thing pretty hard. And by the end of the hill, you'll see all these cars and trucks on the side of the road with their hoods up and steam pouring out of them. They just couldn't handle it, especially the older ones. Modern cars are really, really efficient, right? Unless you come from Kamloops, from the winter time, and the whole radiator is filled with sand and salt, and you didn't wash it out, it's not going to do as good of a job of cooling itself, right? But it still happens. We want to put water in that thing. Is this what we put in the cars, though? Is it water? The radiator liquid. What's another word for that? Especially in this weather, coolant. Another word for coolant is antifreeze. Yeah. So you know, if you put water in there, you don't want to put in straight water. It's going to freeze. And what happens with water when it freezes? Which is opposite to everything you've learned, right? Kinetic molecular theory. When things cool down, aren't they supposed to shrink? Water is one of these weird things that actually does the opposite. Okay? It's strange properties when it comes to water. But you guys know, yeah, it freezes. It can actually break your lock in your engine. Not good. So what we actually do is, what is this stuff called? Yeah, that's antifreeze, ethylene glycol. Okay? Now the specific heat capacity isn't as good as water. So you think to yourself, well, maybe I just want to put in straight water in the summertime. Doesn't that do a better job? It's more efficient than ethylene glycol? Yes, but there's another problem with putting water in your engine. It'll corrode. Even if it's aluminum, you get some electrolysis happening. So ethylene glycol, not only does it not freeze, there's anti-corrosion stuff inside of there, okay, which is what you want. Okay, it says it right there. So anyway, this is specific heat capacities. These are numbers that you want to raise 1 kilogram of substance by 1 degree. Here's a formula I was talking about. Okay, how much energy do you need to raise a certain mass of some substance? That's what C is. This is a table of C's. Okay, these are specific heat capacities. That's given the letter C. C for capacity, so it almost makes sense. Okay? Raised by, well, what change in temperature? You remember what delta means? We saw it with delta V. We saw it with other things, right? That's final minus initial, or you can think of that as an O. So delta T, remember, is the final temperature minus the initial temperature. It's not always going to be 1 degree. What if I want to raise the temperature of something from room temperature, which is about how many degrees Celsius? 20-ish, yeah? Some people, it's been noted that they're most efficient at work if it's 19.6 degrees. So companies like the big ones actually do this, right? Because then people are more efficient. When it warms up too much, they get a little cozy and they don't work as well. When it's too cold, they just sit there and shiver, right? So there's an optimal temperature. They always want maximum productivity, right? 20-ish. Let's say I want to raise it from 20 to 80 degrees. How much energy in joules is that going to take? Well, it depends on the mass, how much you got, right? And it depends on the material. That's where C comes in. So, a couple of examples. I'll do this guy first. This is as basic as it's going to get, because this formula is solved for in terms of the energy. But you might have to solve this for the mass. You might have to solve this for the change in temperature, or what's maybe even hardest, maybe just the initial temperature or the final temperature. Okay, got to solve it for one of those. I'll do that in a sec. So how much heat? Heat's in what units? Joules, right? That's energy. Joules, that's what I'm solving for. To raise the temperature of not 1 kilogram, but 90 kilograms, that's M. C for water is 4,200, and I'm not even going to worry about the units. Make sure mass is in kilograms. Make sure, well, your temperature is going to be Celsius, so you shouldn't have to worry about that. Okay, and then energy is going to be in joules. If it's kilojoules, megajoules, you got to convert it. If you're given grams, you got to convert it. Okay? If everything's in the right units, you don't have to worry about it. Now delta T, remember, is the final temperature minus the initial temperature. Don't forget brackets, of course, or algebraically that's not going to work, is it? So 90 times 4,200 for water, and from this to that. So what am I doing? I'm raising this by 62 degrees, right? So you can put that in the formula, or just think to yourself, what's the change in the temperature? 80 minus 18. Okay, put that in your calculator, and sig figs, that's what I get. What's the unit for energy? Joules. That's the change in the energy. That's how much heat is needed to raise a barrel of water, that's 90 kilograms, from 18, just under room temperature, to 80. Okay? Let's look at this guy. It's done for you, but I'll do it again. 25, what does that say? Kilojoules. What's a kilo? 1,000. Okay, so you can go 25, 10 to the 3 is the prefix for kilo, or that's the same thing, isn't it? I want this in joules. 50 kilograms of water, initially at 20 degrees. That looks like time, big T. That's T initial, or TO if you like. I like I, because, you know, initial starts with an I. What am I trying to find? I'm trying to find the final temperature. Okay? And water, what's the heat, the specific heat capacity? That's 4,200. That's on your table over here. Okay, if it's joules, degrees Celsius, that's all we need. Here's our formula. Okay, but I don't want to write it like that. I want to write it like this. I'm solving this thing for TF. So I could manipulate this formula for TF, but I think most of us would put in the numbers first, so let's do that. So that's how much energy, 25,000 joules. M is 50. C is 4,200. TF, I don't know. And the initial is 20 degrees. Okay, solve that for TF. What would I do first? Because I could multiply this out here, right, to both things, but what would be easier? Yeah, you'd probably make that a single number and then just get rid of it. Whatever you do to one side, do to the other side. So let's just see what that number is. What is 25,000 divided by 50 divided by 4,200? 0.119. 0, so let's just go 0.119 is TF minus 20. Do I need those brackets there? Do they do anything? No. How do I solve that for TF? Add 20 to both sides. That's the final temperature. 20 plus 0.119 is 20.119. And if I'm picky about sig figs, which I'm not, but some teachers are, there's 3, there's only 2. But that doesn't make any sense because it's the same answer, isn't it? So let's just round that to tenths. That's the final temperature. 1/10 of 1 degree higher than what it used to be. Okay? That's quite a bit of water. You think that's quite a bit of heat, 25,000 joules, but that's quite a bit of water. And because the specific heat capacity is quite high for water, that's all it does. Just raises it by 0.1 degrees. Okay? So, something else? Efficiency. Which we've already kind of seen in some of our assignment questions. Just the common sense type stuff, I hope. Here it is as an actual formula. Again, that might seem like common sense. It should. Because as you found out in your lab, energy's not conserved in the real world. At least it's hard to tell that because you're always going to hear things. Some of that energy is going to be converted into sound, even when playing pool. Billiard balls, it's a fairly, the collision's quite efficient, right? There isn't much give between two hunks of, what is a good pool cue ball? I should know this. Is it ceramic or porcelain? Sometimes they're actually made out of stone. Anyway, it's quite efficient, but you're still going to get losses. You can hear that ball rolling on the billiard table, can't you? Even though those cushions are pretty good at bouncing the ball back, you know if you bounce it, it only goes so many times before it stops, right? So some of that's converted into heat in the cushions. Some of it's converted into sound. Eventually that ball stops. It doesn't keep going indefinitely. So this is the definition. What you get out divided by what you get in. If I push that billiard ball with 100 joules of energy, that's how much I put into it. And maybe it bounces back with only 90 joules of energy. 10 of it went to sound, because you hear it. 10 of it went to heat. If you measure the temperature of those cushions after you bounce a ball off it a few times, you would find that the temperature actually went up. What is this when you divide 9 by 10? That would only be a 90% efficiency. That is, the kinetic energy is only 90% conserved. Okay? So, common sense, if I put 100 joules into something and I only got 50 out of usable energy, well, that's only 50% efficient. And it's surprising how many things we use every day that are a lot less than that. It's only recently we got into some other kind of light bulbs that were more efficient than incandescent. Like normally you don't want to heat your house by turning on a light, but that's what we used to do. Not much of the output of an old light bulb went into light, which is the purpose of the light bulb. Yeah, most of it went to heat. Very, very inefficient. Oh, it says it right here. The ordinary incandescent light bulb, you know, the one with the tungsten filament, the one that got invented by allegedly Edison. Okay, he's the guy who actually patented it and made all the money, but I believe it was invented by someone else. But he took all the credit for it. Okay, only 5% of its energy goes into light. All the rest goes into heat. Okay, so efficiency. Let's look at a couple of these. This is a bit of a confusing question, and I'll show you why in a sec. To lift a 1200 Newton motorcycle, what does that say? If something's 1200 newtons, then that is its weight. Yeah, weight, force of gravity, mg. Okay, that is a force. Up a vertical height of 1.3, so we know, let's actually do it here. To lift that from here to here, that's work, right? I've got weight. I've got a distance in the same direction. We know a formula for work is force times distance. But a motorcycle rider pushes it up a ramp because it's pretty hard to lift this bike into the back of the truck, right? So most people get ramps. So this guy pushes it up the ramp 2.4 meters. And it's actually costing him a force of 820 newtons to do that. So is that in the same direction? Is this force in the same direction as he's pushing it up the ramp? Yeah, that's what the question's saying. Okay, so it's a little kind of confusing. Okay, so he is doing this. This thing actually weighs 1,200 newtons. How much work is he doing? How much work is he putting into the system? He's putting in, okay, so efficiency is work out over work in. He's putting in that. That's what he's doing to push this bike up the ramp. Okay, how much work's he getting out? Well, the bike ends up in the back of the truck, 1.3 meters. So the work he gets out is the force of the bike, its weight, times its distance. Okay, so that's what he gets out. So if we do that, come on. Whoop. Maybe I should do these separately. That's 1560. That's the work he gets out. What he puts in, well, it should be more, right? Or can we get free energy? Like some of you guys did in your lab. Okay, 1560 divided by 1968. That's the same operation. That's 0.79. How do I get it in percent? Times by 100. 79% efficient. Okay? So that one's, it's a little confusing in the wording. Let's do a couple more. You must do 500 joules of work. Efficiency, this is on the back of your book, right? Yes. So it's work, but it's also power. Okay, so some other questions you're going to see in a sec, it's power. So when you must do that much work, is that out or in? In. That's the work you put into the system. You did that amount of work. How much did you get out? You lifted 150 newtons, 3 meters. Okay, that's the work out of the system. That might be a little confusing to see which one's which, but you know, if you got them upside down, you're going to get something over 100%, which doesn't make any sense, right? Okay? Your cart should not be going faster, right? You shouldn't have more kinetic energy than the potential that you had, if there's no errors. So what's 450 divided by 500? That's 90% efficient. The formula here doesn't say put it in percent, so 0.9 is also the same thing, right? Okay? A kettle tells us the efficiency. 80% efficient. This is a little more confusing. It's a 1200 watt kettle. What do you think that means? And you have no way of knowing until I tell you. Does that mean you get 1200 watts of energy out of it? Or is that what it sucks from the wall when you plug it in? Yeah. Your 1500 watt hair dryer, that doesn't mean you get 1500 watts of energy drying your hair every morning, right, Calvin? Okay, that means that's what it sucks actually from the wall outlet. That's a lot. Like I know in my house, whoever wired it, the microwave circuit is on the same one as the hair dryer. So when I put my oatmeal in the morning, I hear screaming from the bathroom. Sometimes it's kind of enjoyable. I do it on purpose. Anyway, rated, that's what it sucks from the plug, okay? That is the work in. At what rate does the kettle absorb energy? out. Yeah, I'm just kind of looking at this thinking that's kind of a little bit backwards. So, simple math times both sides by 1200. Okay, 0.8 times 1200 is 960 watts. Now, we need another question here, so I'm going to add it. Okay, 2b. So you need to write this down, otherwise you won't have an example of how to do it in the book. So a 600 watt kettle, what does that mean? That means how much it draws. Heats up 100 grams of water from 5 degrees to 100 degrees in 90 seconds. Is that a good kettle? Is that a slow kettle or a fast kettle? Do people actually rate kettles as to how quickly they can, how efficient they are? I don't think they do. Most people buy them for how they look, right? Like my wife. Okay, what is its efficiency? In one word. So here's our formula. This one now is power, isn't it? Efficiency is power out based on how much power goes into that kettle. So, how much do I put into that kettle? Okay. How much does it give me? Got a lot of stuff going on. Well, I know something about heating up water based on some temperature. Okay, I know I got a mass of 100 grams. Do I want to put 100 here? No, I want that in kilograms, right? So move the decimal 3 spots to the left. That's kilograms. C for water is 4,200. What's my change in temperature? Yeah, final is 100 minus initial 5. I'm raising this by 95 degrees. Okay, so if I do that, I get, come on, 0.1 times 4,200, move the decimal once, times 95 is 39,900 joules. But is that power? No. Is there something that relates energy to power when I'm talking about a time? Yeah, power is work, which is energy, over time. So I got 39,900. My time, I want that in seconds. Divide that by 90. So the actual power here is 443 and a third. What's the unit for power? Watts. That's what I get out of the kettle. So my efficiency, it's sucking 600 watts from the wall. I'm only getting 443 towards heating my water so I can make my tea. So 0.73, let's just round it to the nearest percent. 0.74, which is 74% efficiency. Like I said, it's weird. You would want efficient kettles, don't you? You don't want to waste energy, but how many of them are actually rated this way? None. Not a single one. Okay, I'll leave the other two to you guys. This one's what I was talking about when it comes to cars. So just pay attention when you're, this is actually a truck, when you're doing that question. Okay, it's kind of enlightening. So do the guys on page 61. These two. And a few more. That's it for material for the test. Just give you some more questions tomorrow. Hopefully hand your lab back, and that's it. Oh, I was going to show you something. Hang on. Haha. Where is it? You know how I said you can't get energy for free? You can't get something for nothing? So I thought I'd look it up again, because I know I have in the past. This was just in February. They did it. Who watched Spider-Man? Dr. Octopus? You remember? What was he trying to do? Yeah, he was trying to create the sun in his New York penthouse or whatever. That's why he needed these big long arms to contain the fusion reaction, right? It's not all that far-fetched. That's not Dr. Octopus. But what that is hundreds of lasers which actually did fusion. That's how the sun works. We get fusion. It fuses molecules together and releases huge amounts of energy. They did this in a lab. And the amount of power that it takes to fire all these lasers, there's 192 lasers. They actually got more energy from fusing the atom than they did firing the lasers. So they're making energy. Like, this is cool, right? If we could get this to power the cars, oh, they'd never let that happen. There wouldn't be any tax money in it. Okay, this is plasma physics. Okay, this is a $3.5 billion operation. Anyway, it's cool. Like, they haven't, I think that's the first time they've done that, to my knowledge. Good question. Feel free to read it. Where's this thing? Okay.